Hi, everyone. Thank you so much. So yeah, my name is Kalen Patton, and I'm going to be talking to you today about improved mechanisms and profit inequalities for graphical dependencies. And this is part of joint work with Vasilis, Livanos, and my advisor, Sahil, who's here today. Okay, so the first thing I want to do is kind of put our work into this broader context of looking at stochastic problems beyond independence assumptions. So in many stochastic problems, our goal is to optimize some objective when we have some underlying uncertainty in the form of random variables. And often, what's often the case in these kinds of problems is that we find that if we permit these random variables to have arbitrary correlations, then the problems are often intractable in the sense that we can't get any constant approximation. But on the other hand, if we assume that the underlying random variables are independent, then we can get strong positive results, often in the form of constant order approximations. And so the motivation behind our line of work is this observation that both of these extremes, perfect independence and arbitrary correlations, seem implausible in practice. And so we ask if there's anything that can be done in the setting where only mild correlations exist. And so the main problem that I'm going to talk about today is actually not profit inequalities, but this single buyer revenue maximization problem. Although since this is the profit inequality track, I will be sure to say some things about that result as well. So in this single buyer revenue maximization problem, we have a set of n items, and we have a buyer with a private valuation V sampled from some public distribution D. And our goal is to devise a mechanism, which in this setting can be represented by a menu, to maximize our expected revenue when the buyer picks their favorite menu item to maximize their utility. And as often is the case in these mechanism design settings, we will also make some structural assumptions on the valuation function V. So we can assume a few different settings for V, that V is unit demand, additive, or in this most general sense, we may only assume that V is subadditive. Okay, and so far I haven't specified any assumptions on the distribution D that the valuation is sampled from. And this can be thought of as, in this most general setting, allowing arbitrary correlation between the buyer's valuation on different items. And what we find, though, is that in this most general setting, that it's actually intractable to even come up with any positive factor approximation of the optimum revenue with a bounded size menu. So instead, we might look at the setting where the item values are assumed to be independent. And in this setting, it's still the case that we can't explicitly compute the optimum menu, but we can get constant factor approximations. And through this line of work here, we actually know that even in the most general setting where we allow the valuation to be subadditive, we can get these constant factor approximations. And in fact, we can do so with just some very simple mechanisms. So the main mechanisms that we'll talk about today are these separate pricing mechanisms, assigning a single price to each item, and this grand bundle pricing, where we just assign a single take it or leave it price on the entire item set. And we'll also denote the revenues of these two mechanisms by SREV and BREV respectively. Okay, and to put the previous results from the previous slide sort of, oh, yes.
What do you mean by independent and subadditive? How you draw the evaluation?
Sorry, say that again.
So how is the valuation independent and subadditive? Like you draw for each subset?
Yes, so that's a great question. That's something I intentionally kind of glossed over. Yes, we have to be careful because now just knowing item values doesn't immediately determine the entire valuation function. We have to do something a little bit more nuanced, I guess. We come up with some possible item sets for each. No, sorry, let me take this offline. But yeah, I'll answer it at the end, perhaps. Okay, sorry. So anyway, where was I? So I was trying to say that these results from the previous slide about independent and arbitrary correlations on items can be represented pictorially by imagining this kind of continuum over item distributions from independent items to correlated items. And we see that in the setting where we have independent item values, we can get these simple constant approximate mechanisms, but when item values are arbitrarily correlated, we essentially can't get any approximation factor with simple mechanisms. And so our line of work is motivated by this question of what happens here in the middle? And in particular, to answer this, how do we even quantify correlation strength in the sense of where different distributions lie on this spectrum. And so before I get to our model for this, I'll just mention that some work has been done on different models of correlations in the past, including linear correlations or pairwise independent distributions. But for our purposes, these don't quite capture what we want, which is some way of modeling this full spectrum from independent distributions to arbitrary correlations. So the model that we will look at is this model of Markov random fields, or MRFs. And this is a graphical model of dependencies in high dimensions, which has been used to great success in fields like statistics, physics, and machine learning. And I won't give the precise definition of these Markov random fields, but I'll try to give a rough sketch of their structure. So essentially with these Markov random fields, we have some random vector, and the coordinates of this vector have correlations that are modeled by some weighted hypergraph over different data. So for instance, if we imagine a buyer's whose valuations on different items are represented by these MRF entries, we might imagine that the underlying hypergraph looks something like this, where similar items like these fruits over here have edges that induce positive correlations between their values, and dissimilar items like an orange and a cup of coffee have edges that induce negative correlations. And this model works very well for the questions we're trying to ask because it allows us to use this graph parameter of this weighted maximum degree to bound the correlation strength in these MRFs. So what I mean by that is, for instance, if this weighted max degree is 0, we recover the independent item settings. And if we allow this weighted max degree to tend to infinity, then we can model arbitrary joint distributions with these MRFs. Okay, and so we're going to look at this problem with mechanism design with MRF dependencies, but we are not the first ones to look at this problem. In fact, it was first proposed by Vasilis and Daskalakis in the context of learning the optimal menu. And then later in this work by Sahil and Okonobu, the performance of simple mechanisms like SREV and VREV was studied and compared as approximations of the optimal revenue. And what they found in this work is that max SREV and VREV is an e to the order delta approximation for an additive or unit demand buyer. And along the way, they also derive this e to the order delta competitive profit inequality. And these are great results because these tell us that in the setting when delta is 0, we recover the constant approximations that exist for independent items. But these results still leave some open questions because the best lower bound shown in this paper was for the mechanism design question was on the order of delta to the 1/7. So there's kind of this exponential gap between the upper and lower bounds as a function of delta. And also another thing we might ask is why is this e to the order delta term appearing in these approximation factors? And the short answer is that's due to this kind of MRF conditioning property, which says that if you look at one entry in our MRF and we look at its marginal distribution, when we condition that marginal distribution on the values of all other entries, it can change by at most a factor of e to the delta when compared to its unconditional distribution. And this e to the delta is what essentially induces this e to the delta factors in our approximation. Okay, and so this brings us to our result, which can be broadly summarized by stating that we find that this e to the delta loss in the approximation factor is actually not necessary. And so we can get these approximation factors that are linear in delta for the single item profit setting and for the additive and unit demand revenue maximization setting. And in fact, also we're able to extend this all the way to the sub-additive case, which matches the results for the independent items as well. And so this is very nice in terms of bringing the upper bounds much closer to the lower bounds for these dependent item settings. So for instance, for the profit inequality result, we actually know that this order delta is tight. So we have also a linear in delta hardness example. And for revenue maximization, we now only have a poly delta gap to this lower bound of delta to the 100%. Okay, and so with the remainder of my time, I'm going to try to give some idea of the new proof ingredients that we use to get this improvement. And to understand them, it will be important to have some understanding of the proof techniques in the independent item settings. So I'll try to give a rough sketch here. So most of these independent item results showing that revenue is bounded up to a constant by SRev and BRev come from this core tail decomposition approach. So essentially, we partition the item set into a core set consisting of low-value items and a tail set consisting of high-value items. And the reason that this partition helps us is because of this so-called marginal mechanism lemma, which allows us to bound the optimal revenue by the sum of the value of the core and the revenue from the tail. And then by carefully choosing sort of the cutoff between the core and the tail, we can get these two nice properties on both sets simultaneously, where the tail is sparse enough that most of the revenue can just come from selling one item, which allows us to roughly get that its revenue is bounded by SRev, and that the value of the core concentrates because all items in the core have relatively small value and have an independently distributed value. So some concentration result like Chernoff bounds allows us to say that the value of the core never deviates from its expectation by too much. And that means that we can guess a price for the grand bundle that achieves like a constant fraction of the core's value. So then when we try to take these tools and adapt them to this correlated item settings, we immediately run into some problems. So first of all, for this marginal mechanism lemma, this lemma crucially only holds for independent items. So we don't necessarily know immediately how to use this for dependent items. And although there are some generalizations for dependent items that have been proposed in the past, in this setting, they cause us to lose an e to the order delta factor due to some conditioning. And then the second problem we run into is that this core value is now much harder to control. So first, the value of t that we need to set, this threshold, suddenly increases by a factor of e to the delta in order to get our nice sparse condition for the tail to hold. And then, so not only have the item values of the core increased by a factor of e to the order delta, but concentration itself breaks down because the items are no longer independent. And so the way we handle these two challenges is we have these two new ideas, where first we have a new marginal mechanism lemma, and next we're able to use some exponential bucketing trick to handle the increased value of the core. And okay, so let me try to say a few words about these. So for the new marginal mechanism lemma, essentially we can get something similar to the marginal mechanism lemma for independent items, but just losing a factor 2. And the nice thing about this lemma that we propose is that now this holds for arbitrary distributions D. And for our exponential bucketing trick, this comes from this observation that if you look at certain statistics on MRF distributions, statistics being things like the mean, the variance, the cumulative distribution function, we find that they have similar properties to product distributions, similar values, but losing an e to the order delta factor. But here, losing e to the order delta factor is okay because we can handle that by using some adaptation of the threshold algorithms that are used in independent items. So I'll explain a little bit more about these in a moment, but essentially what we have is that if we have a threshold algorithm for an independent item, which offers a single threshold at tau, then we can convert this into a threshold algorithm for MRF distributions by sort of blowing up tau by a factor of e to the order delta, and then guessing one of these exponentially spaced thresholds in between. And the main idea here is that one of these thresholds will be good for us, and because there's only linear and delta many of them, we have roughly a 1 over delta chance of guessing the correct threshold. And this comes into play for our profit inequality result and our price of the grand bundle. Okay, so let me try to say a few more things about each of these. So first, our new approximate marginal mechanism lemma says formally that if we have kind of two disjoint sets of items, A and D, and we have an arbitrary distribution over subadditive valuations on this joint set A union B, then the optimal revenue of selling these items to a buyer with valuation V is just exactly what I mentioned earlier, 2 times the value of A plus the value of, plus the revenue of B. And this seems pretty innocent at first. It seems rather uncomplicated, but its value can be seen if we compare it to a similar lemma by Rubinstein and Weinberg, which also gives us that the revenue of our joint set is bounded by the value of set A. But we have also the revenue set B conditioned on the valuation function on A. And this is the conditioning that I was mentioning earlier that causes us to lose an e to the order delta factor if we just use this kind of lemma out of the box for our purposes. And I won't say too much about the proof of this new lemma, but roughly speaking, it's based on some kind of discounted argument where we take the optimal revenue on the whole distribution, restrict it to B, and then discount prices by a factor 2. Okay, and then a few things about the exponential bucketing technique. Remember, the idea is that we convert a single threshold strategy for product distributions into this kind of randomized threshold strategy for MRF distributions. And the threshold strategies that exist for product distributions are, for profit inequalities, there's this classic single threshold at the expected max over 2. And for grand bundle pricing, I'm thinking of this as kind of a threshold strategy, since we only sell the grand bundle if the buyer's valuation is above our threshold or our price. And so here we're imagining the grand bundle price at roughly the value of the core over 2. And then the rough idea for why this exponential bucketing trick works is that because we have now our smallest threshold at our original threshold price and our largest threshold at a price e to the order delta larger, we can still bound the amount of value that we lose if our sort of if our hindsight optimum, our sample opt that we're trying to approximate, falls below the lowest threshold or above the highest threshold. Because these are separated by a factor e to the order delta, we can do this, we can bound this loss even in spite of our MRF dependencies. And then if this sort of sample opt lands in between the two thresholds, then there we have a 1 over delta chance of guessing kind of the correct threshold and getting a constant approximation. Okay, so to wrap up and bring it back, broadly speaking, we're studying 2 problems in this general framework of looking at stochastic problems beyond independence assumptions. And we're using MRFs as a nice model of this continuum from independent distributions to arbitrary correlations. And what we find is that for these problems of single item profit inequalities and single buyer mechanisms, we can get an approximation factor that's linear in the weighted max 3 delta. Our contributions are this new marginal mechanism and this exponential bucketing trick, which works particularly well for these threshold-based algorithms. So I'll leave you with just broadly speaking, our future directions are that we're curious about what other types of stochastic problems can we apply this framework to and get good approximations for in these settings with mild correlations. Great, and that's all. Thank you so much.